Hello, good afternoon. Welcome to today's presentation. My name is Philip Taylor. I'm Hydro International's product specialist in stormwater for the Americas Stormwater business. The presentation today is going to be themed around the Specifiers Toolkit and decoding the BMP sizing mystery a little bit. Hopefully you can all hear me and there's not too much background noise. If there's any real issues, please just ping me an instant message on the system here and I'll try and address it. This presentation, there will automatically be sent out certificates of attendance to all registered attendees. So if you signed up and attended this course, within a week or so you should see a certificate of attendance sent out to you. We had roughly almost 300 people sign up for this course, and currently we've got about 132 online. So it's a good turnout, and I thank you for making this time to listen in today. You just have to bear with me a little bit as the technology catches up. Just wanted to check that we are recording this. The button hasn't appeared on my, okay, recording in progress. Okay, so at the end of this presentation, there will be a short survey, and I'd appreciate it very much if you fill that survey in. There's also a place at the end of the presentation where you can write questions and comments. So if through this presentation you have a question or a comment you'd like to make, please just fill that in as part of the survey and we'll pick that up. Any questions regarding any technical aspect of the presentation, questions you have, fill that in and I'll address those this afternoon or tomorrow, early morning. As I say, this this presentation has been recorded. When we finish doing the recording, we put it up on our Hydro International TV YouTube site, so you'll be able to view it later on. Also attached, you can see there is a download option where you can get attachments for this presentation. I've included some product brochures and a PDF copy of this presentation for your use as well. So just an overview of what we're going to talk about. I'm just going to introduce Hydro International. I'm going to talk about what exactly is sizing. Talk a little bit about local regulations, approvals, particle sizes, sizing methods, sizing tools. Do a little bit of a demonstration on one of our sizing tools, and then just sum up what we would have talked about. And that should take about, I would think, 35-40 minutes. So this will fly by, hopefully, for you. So a little bit about Hydro International. Hydro is a smaller company, but we've been around a long time. 30+ years experience in structural BMPs and also wastewater treatment. We have installed thousands of separators and filters around the world, and we have a great deal of opportunity. We have a world-class lab within the company, so we can do a lot of testing and development within our own company, which allows us to rapidly develop and produce new products. So we do business in about 33 countries around the world, about 200 employees. Our primary stormwater market in the US is managed from the Portland, Maine office. Our wastewater and wet weather flow office is located in Hillsborough in Portland. Now, we specialize in water treatment, so we do stormwater treatment, wastewater treatment, combined sewer overflows, and a lot of the technology overlaps and has similar purposes and similar looks to it, but applied to different parts of the industry. We also do a lot of collaborative work, working with universities and other institutes to develop new products, to verify products and make sure that everything is doing what we think it does and works in the field. And to do that, we go out and we get certifications with lots of the DOTs, the local regulators, the PCA, so that we can assure people that what we produce is well tested, well researched, and then validated and verified through the third-party processes. In our stormwater line, we have 5 primary products for stormwater. We have 2 separators. We have our downstream defender and first defense unit. We also have vortex flow control and flood control valves, a screening BMP for gross pollutants and trash, and also a filtration system called the upflow filter for filtering of stormwater for removal of very fine particulates and dissolved phosphorus and nutrients. So to start off with, I just want to get a bit of a feel for the people out there, yourselves, and what your familiarity with this topic is. So I'm just going to run a quick poll just to see if anyone's listening. And I'm just going to run that poll now. So I'm just launching this poll, and if you could quickly throw in a few answers there. I won't have this poll open for too long, maybe 20 or 30 seconds, just to give us a bit of a trend. There'll be another short poll after this one, and that'll be the end of the polls. Okay, we're just about done. So that's about 30 seconds. I'm just going to close the poll now. We've got about 80% of the people who have voted. So I'm going to close that poll and share that with you. Now, as you can see, roughly 70% of the people online would need to do some research before they could size a separator to their local regulations, with about 30% looking like they're very familiar. So, and there's a small portion there where the local regs don't allow it or not allowed. So there's obviously great opportunity to learn here. So hopefully I'll be able to help you out with this. So I'm going to move on to the next slide here, hopefully. And the second poll. If you are sizing separators, how would you get them sized? So I'm just going to run the second poll now. Again, I'm just going to keep this open for about 30 seconds, and then I'll share the results. Okay, I'm going to close the poll now. Share the results with you here. This is a little more interesting result. 28% people said they do the design independently, and about 37% there say they would call the vendor, and about 30% use the vendor software. So it's fairly even split on how these things get designed. This is actually one of the key components of this presentation, is how to get designs done and to look at the sizing aspect of these. So now I'm going to move on with the presentation here and talk about regulations. I'm going to go through a whole process of slides here. There's quite a bit of information to cover. So when we talk about pollutants in stormwater, these cover things like total suspended solids, or TSS, nutrients like phosphorus and nitrogen, pollutants that float like hydrocarbons and trash. There's also other pollutants in there like dissolved or particulate metals and other stuff like that that really are more difficult to remove, that are covered more by an industrial stormwater permit. For this presentation, we're primarily talking about the MS4 permit and the municipal type permit. And as you can see, stormwater isn't discriminatory. It will carry whatever pollutant we throw at it and bring it down into the storm sewer system and into the receiving waters. So the BMPs that we put in place have to deal with not only a range of pollutants, but quite a range of stormwater conditions, flows, and that sort of thing. So they're asked to do a lot for a passive system. So when we look at a toolkit for engineers, the target pollutant really starts the conversation on what the equipment or the solution will be. So if we're looking at gross pollutants, things that are bigger than, say, 1/16 of an inch or a 1 millimeter size, these include sort of the coarse gravels, the coarsest, very, very coarse sands, trash, leaves, all the big stuff that floats, then screening is probably an appropriate BMP. And the things about screens, they can often be used with big pipes, big flows, and can treat quite large amounts of water very easily. But as we move to the left of the slide, and we move into the finer particulates, the coarser solids like coarse sands to very coarse sands, then that's where hydrodynamic separators start to perform well, down to about 100 or so microns. Then when we move down to the much finer solids, things in the range here of, say, 20 to 100 microns, that's when we're starting to really move into the area where you've got to start filtering stormwater, you've got to start using settling ponds, wetlands, where the water is actually either strained or retained for a reasonable period of time to allow these solids to fall out. And then we get into the area of what we call non-settleable solids. That goes into the sub 20 micron, and the dissolved solids, which goes into the sort of 0.45 micron and below. These are very difficult things to remove, and that's when we start looking at chemical and biological processes. We start looking at very expensive systems. So the pollutant itself, to a large extent, will dictate the solution that you have to look at. So primarily in this presentation, there's too much in that previous slide to look at in the totality. We're just going to look at the separators. These are some of the most common proprietary systems used in the stormwater market, and the sizing of these separators and the toolkits available to those, how they're assessed and how they're used. So when we look at stormwater treatment, we're looking at treating water, and because this is generated by rain, we have actually two considerations here. We have a treatment flow, and that's the flow that we believe the bulk of the pollutants are carried in, and that's what we're targeting in terms of the capacity and the purpose of our piece of equipment. Then we have the peak storm flow and how we handle that, because A, we want to be able to hydraulically pass or handle that peak flow, and B, we want to be able to retain everything that were previously captured when that peak flow occurs. So those are two important considerations when you are looking at a stormwater treatment system. And just to understand a little bit of how these would physically fit into a system, when you look at an online system, typically your separator is placed in the pipeline, and it must convey both the peak flow and the treatment flow, as well as handle the pipes in any other situation and the site arrangement. So that's what we know as an online system. The other way we can do things is we can go offline. Is that where we place the system off to the side of the main stormwater line, and we just divert the treatment flow to it. Now this is a good way of sizing the separator purely to the treatment flow. So we're not trying to size it to treat a peak flow, and we also protect it from the peak flow by having an external bypass. Many regulators require the offline installation as standard. Some allow an online and offline system, they don't care. Some will only allow an online system if sufficient testing has been done to prove that the equipment will not wash out at its peak hydraulic capacity. So there are lots of different schools of thought around the online and offline arrangement. And then we have the system where you have an internal bypass, so it's online, but it has the internal bypass to effectively remove it offline. This is, again, it's a compromise when we do this. What we're trying to do here is make the system do everything. We're trying to make it remove particles and trash at the treatment flow. We're trying to pass the peak hydraulic flow. We're trying to minimize the number of structures we're using. We're trying to stop it washing out. And this is a conundrum for many product developers when you get to a system like this, because you have to juggle several different objectives. You can make one that can pass lots of peak flow that treats very little flow, and it might work really well, but it will only treat a very small flow and become a very large system. You can make one, you can alter the bypass condition so that you can treat a lot of flow, but bypass a small amount of peak flow. So it's this three-way sort of bypass flow, peak flow, and head loss equation, which sort of makes these online systems a little more tricky, these internally bypassing systems a little more tricky to develop. And then you have to go to the real world and understand that sites can be complicated things. And when you start looking at the physical arrangement of the site, how much water runs in every direction, where all the pipes are, how deep the pipes are, where all the utilities are, and also where you need to place it for maintenance, a lot of consideration has to go into what system you use. Often, it's actually more effective to put 2 or 3 smaller systems around a site than trying to bring everything down to one end of pipe system. When you start making these things bigger, costs escalate, cost of installation escalates, and costs of maintenance escalate, and having 2 smaller systems located throughout the site is often more efficient in terms of a long-term ownership cost than one big system downstream. So these are the things that need to be considered as well when you're looking at separator or treatment design. And one really important aspect, this is where the industry in general, all of the stormwater treatment industry, is just starting to get its brain around, and that is maintenance. You've got to design these for maintenance. You've got to design any stormwater BMP so that it can be maintained. There have in the past been many stormwater ponds built and houses put all around them, and now they're coming up after 20 or 30 years for major maintenance, and they find that you actually can't get a truck and an excavator to the stormwater system in the back of people's backyards, and they're having to build new systems to compensate for the development that's gone on. So when we look at these systems, it's critical. Without maintenance, all this falls over. Maintenance is actually the key BMP of the whole system. And we're seeing a number of underground systems being designed that, for practical purposes, the access for maintenance or maintenance of an underground system could be very difficult. So this is an area where a lot more study is being done. So local regulations. This is another problem we have in the industry when we come to developing equipment. Everyone has a slightly different idea of what they want. Traditionally, the rule was, oh, we want 80% total solids removal. And then some people started looking at the total solids and going, really, we should define that because is it 80% of sand? Is it 80% of silt? Is it 80% of gravel? They're all correct. But what is it? And then we have more defined regulations, like the second one there, 90% of TSS based on the NERP curve and 60% of total phosphorus. This is something we see in Minnesota. So they start to really define more closely what it is. Regulations like matching pre-development total phosphorus and total nitrogen to got to match the post-development to the pre-development conditions. In some areas, we have to control the effluent to a limit, like 30 milligrams per liter, and this is one we see in Colorado and Denver. There are many regulations where you just have to mimic your pre-development conditions, either the pre-development runoff coefficients or the pre-development runoff flows and pollution levels. 80% TSS based on OK 110. This is something we see around the Midwest within Indianapolis, Indiana area, and the city of Indianapolis has a regulation based on that. We go to California and they want 100% trash capture. So we see a lot of regulations around trash capture. So they vary from state to state. And what's happening now in many of the states, well, what I've noticed is that to make things simpler for everyone, some states are developing standard design models. Now in Wisconsin, it's the WinSlam program, and you have to model your site in WinSlam, and it does all the number crunching, the BMP design, and produces the answer so everyone's on the same page when it comes to assessing a site. In Florida, there's a program called BMP trains. In Minnesota, there's the Minimal Impact Design Standard, which is another software model they've developed. And I think North Carolina, they use the SNAP model, the sizing, I think, for nitrogen and phosphorus models. So state regulators are now starting to develop tools that we must provide information for to be able to model our systems in these tools. And then we have certification processes or people like New Jersey Department of Environmental Protection and the Washington DOE, which are probably the most common, actually worldwide recognized testing authorities and approval authorities that actually certify the performance of BMPs. So when it comes to approvals, testing, validation, certification, as I say, Hydro has a high-quality lab. It's a world-class lab that allows us to do a lot of the pre-testing and characterization before we send our equipment out to third parties for validation, so we know very well how what we expect the performance to be. That's one of the advantages that Hydro has, and we're very proud of that lab and the people that work in it. And when you're given results, now this is something as an engineer, you may be given a data sheet from a vendor on their product and they say it's the best thing since sliced cheese, and you come and they send you a data sheet and it might say something like up to 96% removal. Now the data that you see on this slide is actual data we pulled from one of our systems in Florida. It's for metals removal. And we were doing some investigation trying to characterize the performance of a certain media we were testing. And after about 30 storms, we had all this information, we plotted it up, and as you can see, I could claim up to 96% removal, but it's a little disingenuous when you see wording like up to removal, because you really want to see the bulk of the data. I could also claim, well, on average it was 50%, which is true. As well, which might seem a pretty good number, but in reality, any particular site could be from 0 to 96%. So if you happen to roll the dice and put this on your site and get 0, you're not going to be very happy, and if you get 96%, you're going to be pretty happy. What changes is site chemistry. So site chemistry has a big influence on the performance of many BMPs when it comes, especially to very fine particulates and dissolved nutrients and particulates like copper and zinc and lead. So there's a lot that goes into these BMP designs and study. So when you see data sheets from vendors, always read carefully and look at the background data, make a fair assessment for yourself that the information that you're getting really reflects reality. Now last week, actually, I was in Minnesota attending a Minnesota Erosion Control Conference, and the guys in Minnesota are doing a lot of study on existing BMPs. They have watershed districts in Minnesota. The watershed districts are financed through stormwater utility fees, and they are tasked with controlling and regulating the water quality for the stormwater runoff in their watershed district. So they've spent millions of dollars over the last few decades on improving water quality, and they've had some success, and they've been studying the success and going, well, really, it's not as good as we thought it was. We're not as far forward as we thought we were. And so they're starting to study the existing BMPs that have been in for a long time and said, just what's going on? Because a lot of these models that we use model what happens on each side of a BMP. So if you design a pond, you design it on a certain particle size and you size it for how much settles out, and then you think, yeah, great, it'll remove 100% of all particles bigger than 10 microns. There's my pond size. And based on that, you can say, well, I'm getting a certain level of phosphorus removal because I know how much particulate phosphorus is coming in. But what they've done, some studies up there, and they're actually working out that a lot of these BMPs are actually doing conversion processes inside them, so that you get this mixture, like you get 100% of the phosphorus coming in. It's roughly a 50-50 split between dissolved and particulate. It goes into the BMP, and the same load's coming out the other end, and so what's going on? And the BMP itself is converting the particulate phosphorus to a dissolved form through the year and then exporting that. so that you're merely converting the problem rather than removing it. So there's a lot to learn still in the stormwater industry. This is all very recent research, and it's becoming quite startling that many of these large wetlands, ponds and the like are really turning into converters of phosphorus or nitrogen, and so there's a lot going on there. And then we have other unintended consequences going on. The birds don't know that this is a stormwater treatment system. To them, this is a really convenient pond to stop at on their way south or on their way north and spend a bit of time hanging out with all their mates. And you can imagine the phosphorus nitrogen load going in on this and what form it's in. This is just the unintended consequence of building a pond where there never was one. So this sort of thing, you'd study this and go, really, we're going to need an additional BMP on the outlet of this, probably to avoid exporting a huge load of nutrient into the receiving watershed. Okay, so lots of testing is going on. It's part of this industry. Really, the manufactured stormwater BMPs are probably one of the most studied and tested products to date, because everyone you can put it in a manhole, you can test it, it's easy to test in the lab, and we live and die by our test results. So we've been testing these things for decades, so we have a pretty good handle on how they're performing and where they're not performing. Validation is an important part of that. So you do all your testing, and I can produce a dozen test reports because I have a lab that I can set to work, say, test this, test that, and give me a test report. These reports really need to be validated for scientific and statistical validity. So if we do a test report, we can put together a report and put it out to people, and they're happy with that, and they can look at the data and decide for themselves. But what we like to do also is every now and then we put a lot of data into a company like New Jersey Corporation for Advanced Technology, and they will look at the test and validate it. They will often supervise it and produce a database of third-party verified test reports. And you can go to New Jersey, the njcat.org website, and pull a lot of these reports for yourself. And this is a great way of going back to the source data and just checking that, maybe a data sheet you've been handed has some origin in reality, or some origin in a valid test. Certification. Now this is the next step. There's a lot. Validation is a really good thing to get when you get a test report, or you get someone come in saying, we're the best thing since sliced bread, and we've got third-party validation. It's been supervised and verified. That's really good. The next step beyond that is a certified product. Now, there are a number of places that certify the performance of a product. Now, New Jersey DEP take the NJCAT data, and they will certify the BMP to a certain performance level. Washington DOE on the West Coast do a similar thing, but through a completely different process. There are places like the city of Indianapolis which have a table of BMPs. They list the BMP and they state its flow rate and what the performance is. And that is used as a design standard for their area. And there are a lot of places that hitch their wagon to that and say, use that table, but here's how you do the sizing. So a certification isn't in itself a sizing method. It's merely a certification of the level of performance for a certain set of conditions. So, for example, in New Jersey, they certify separators for 50% TSS. It's based on a specific New Jersey calculation. It's a weighted removal calculation, and that's what we target, 50% TSS. If you want 80% TSS in New Jersey, you have to use a filter. It's just the way the testing is. But it doesn't mean that a separator can't remove 80% TSS. It just means you've got to look at how the testing is done and work out how to get there. This is one of the areas that's a little bit of a problem we see at the moment. When we look at our major clearinghouses like New Jersey and Washington DOE, separators are generally tested for 50% removal TSS because that's what their local regulation requires. There are other areas that say, no, we actually want 80% TSS, but we want you certified through New Jersey or through Washington. Now this becomes a disconnect because you'll look at New Jersey and go, but you're only certified for 50%, but we want 80%. So you have to really get to know, this is a situation I've talked to a number of regulators on, how the testing is done and how to back out that information. And here's an example of having detailed testing and knowing the performance of your equipment. There are manufacturers out there that develop a piece of equipment, they do some testing, and they throw a bulk load of material in, and they get an answer, and they think, great, that's our answer, and we hang our hat on that. But they really might not know the performance of their BMP. Now, this is something extra that we did. When we did testing for New Jersey, and pretty much everyone does testing for New Jersey, where you can measure what you put in and you measure what comes out, and the difference is your performance. And you can do that as a single grab sample and just measure the total mass. What we did is we measured the mass of every particle size we put in, and we measured the mass of all the particle sizes coming out, so we could actually section out by particle size what the performance was at different flow rates. Now, this table here is the approved flow rate that we were approved for our first defense, which was about 1.56, I think 1.6 CFS. So at that flow rate, when you look at this, anywhere from about 1,000 microns down to 500 microns, that's pretty big stuff. That's easy to remove, and we did. You get about 100% removal. And again, 500 down to about 250, 100% removal. Now, really, down to about 150 microns, you don't need much of a BMP, because that stuff settles in seconds, and all you have to do is stop it resuspending and washing out, and you've got it. A bucket with some sort of protection system in it will pretty much do that. Once you start getting below the 150 microns, this is where the BMPs start to show their colors and how well they perform. And down to about 50 microns, and this is pretty consistent, these manufactured swirl separators do pretty well. And that's what we see here. So if we go down to about 50 microns, you're going to get pretty good removal. Once you drop below 50 and head down to 20 microns, and we've known this for years, swirl separators would have to be enormous to work in this area. So from a practical point of view, and everyone wants the smallest one they can get, anything below 20 microns, or in that 50 to 20 microns, you're really starting to look at filtration. And we found this was consistent with different pieces of equipment we tested, that at the 50 micron range, that's when about these separators really start to struggle. So under the New Jersey testing, we take the whole sample and we do a series of tests, and we do a calculation. We don't have to get 80%. In this test, 46% was enough. The way it goes into the calculation, we ended up with overall, for all our different flow rates, 50% removal. But if I was in a different area saying I want 80% TSS, if I look down to 50, where I actually performance stops, around about 50 microns, you're getting about 94% removal. So it's a pretty high removal rate down to that 50 micron range. Now, why is that important? This is where we relate to local regulations, and we can help you with that if you have a local regulation you're trying to meet. In Wisconsin, where I am, you can tell from my accent I'm from Wisconsin, right? I gather everyone understood that. The standard is the NERP curve, and the median particle size in the NERP gradation is around 8 microns. It is tiny. The only way you can remove 80% of this is through filtration. In Minnesota, they use the Midwest NERP curve. The median particle size is around 30 microns, 35, 36 microns. Again, that's a really difficult thing to remove without going to filtration or infiltration, bioremediation, that sort of thing. When I go to New Jersey, they use this New Jersey test sand, and its average particle size is around about, or the median particle size, I should say, is around about 63 microns. And this purple line here is OK110, which is used fairly commonly in many states. 110 micron is a common test sand, the old OK110. Its sizing is not too different, but it's a very narrow particle size distribution of about 75 microns up to about 150, 200 microns. So it's a very tight gradation. So even though these two, the New Jersey and the OK110, appear close in the middle, they're quite different overall. So if I'm going to, now that's the important thing. The average, the median there is about, on the OK110 is about 75 micron. And when we go to our New Jersey testing, we find at 75 micron, we're removing over 90%. So that's how I can demonstrate that 50% certification in New Jersey can actually translate to 80% certification somewhere else if we can show the particle size distribution. So the two can be the same, which is a useful thing when it comes to, but you've got to really study your device. You've got to be able to produce this data and have it validated so that you can use this equivalent with certainty. And that's what we like to have. We like to be pretty sure that what we're doing and what we're saying is correct and that we're not misleading people, because at the end of the day, we really want to improve water quality. So that's probably enough of testing certification. I'm going to look more at the tools now and the sizing methods. Within this industry, there are two primary sizing methods. One is called the flow rate sizing or event sizing, and that's where you take a big bite of the problem and you size to grab the whole problem at once. And the other one is net annual sizing, where you kind of slice everything up into small bites and you attack it in a series of small bites. And I'll explain how these two work. So most stormwater manuals these days we find either refer to, they're starting to include manufactured systems within the manuals. As they do revisions, they recognize that manufactured systems are part of the solution, part of the toolkit, and that a sizing method is often appropriate. Traditional manual writing, they usually work on a water quality volume, and these things are not volume based, they're flow through systems, so you have to convert that water quality volume somehow into equivalent flow through rate. So with the event based sizing, and typically we see the event being set at either something like a 1/2 inch runoff depth or a peak runoff from a 1 inch or 1.2 or 1.3 inch rainfall depth. It might be storm intensity. This is the peak storm intensity of 0.6 inches per hour is one they use in Colorado. 2-year storm runoff depth or something like that is usually described within the stormwater manual, and you can go to something like HydroCAD, generate a TR20 design for your site, and you end up with a number. And this becomes your peak treatment runoff rate. So there's that 1.3 CFS, 1.13 CFS in this case for this site, little site, just under an acre. And you can take that number and say, okay, that's my flow rate that I've got to treat, and I want to remove 80% TSS. And you can go to the vendor and get either a sizing table, a certified table, and go, okay, 1.13, I get about 90%, so in this case a 4-foot first defense or downstream defender would be the appropriate device. So that's a simple way of sizing. Or you can take that same data and refer to a pre-approval table like the Washington DOE or the NJDEP and simply select from that table the appropriate device that equates to the stormwater system, so the flow rate. So in this case, it's going to be a 4-foot downstream defender, would need to be 1.3 CFS, that's fine. You might go to a storm scepter 4800 there, or Vortechnics 3000, etc. So these sizing tables are available through these third-party websites. So that's a fairly simple sizing method, and I like it because it works on a peak runoff rate, and it doesn't matter whether that water comes from rainfall or from snowmelt. It's sized conservatively. The net annual, this is often written into many stormwater manuals as well. I see the wording must be designed on a long-term average basis or a long-term rainfall basis, and what that really means is that you take a rainfall record of several years or decades and you sort that record into different intensities. So over a long period, say 10% of the rainfall is of a very low intensity and so forth, and it builds up. And you run all these rainfall events through your calculation. And you end up with a table like this. Now this is typically a third-party vendor sizing tool that you would use for this. You would select your rainfall station and it would come out with all the different intensities, and it would have the distribution of those intensities over the rainfall record. You would then use something like the rational formula, take that intensity for your site, convert it to a flow rate. You would work out what the efficiency of your device is at that flow rate. So at 0.04 CFS, I'm 94% removal of TSS, and then multiply that by the fraction of the total rainfall in that distribution and get what they call a weighted removal. And you just do that calculation for each band of increasing intensity and sum up all the weighted removals to get to a final removal of 94%. And this is a valid sizing method, but it can be heavily skewed by this rainfall distribution. And in many areas, we have a lot of weighting towards the very small rainfall events. And there's more study needed here, because when you do a net annual sizing, it doesn't discount those storms that don't produce runoff. So this is theoretical, really, that a 0.02 inch intensity, which generates 0.04 CFS of flow, is actually running off through your system and transporting sediment with it. So in theory, I've got 5.5% of my total pollutant load there, but in reality, maybe nothing's run through my device yet. And that might happen for quite a number of these storms, up to around about somewhere about 0.2 inches, where I actually start to generate sufficient energy in the watershed to pick up and transport the sediment. So there's more study to be done on this sizing method. I'm not entirely convinced it's really sizing correctly, but it will generally be accepted in many areas. So key considerations on that net annual sizing. Most stormwater vendors who produce sizing software will size on a net annual basis. The other concern is a lot of that, no one vets the sizing methodology and no one vets the calculation or the particle size distribution used in the software. The equipment's vetted, but no one's connecting the equipment and the testing to the sizing tool. So that's something that has yet to be addressed. Some sizing models that vendors are giving are based on theoretical mathematical models as well, that they're not based on actual test data. Within our own models, we tend to take the test data and convert that to an equation for that device, and we use real test data, not mathematical models. And also the net annual sizing model doesn't account for the proportion of days where it's not raining, and this is a cold climate issue, and the sun is shining, and you've gone up to 50-something degrees, and you've got piles of snow on the side of the road full of sediment, and it's melting like crazy, and you've got 2 or 3 CFS of runoff going down your pipe, and no rain. And that's your pollutant load for the season, and you haven't sized your device for that load. And when you look at this on a long-fall rainfall record, when we look at sizing on a net annual basis, it's heavily influenced by these small storms, so you end up with a piece of equipment that's sized, say, to treat this area here. When I size on a peak or event, I might size on a 1-inch rainfall. I size and end up with a piece of equipment that's set to treat this rainfall to 80%. That means that everything to the left I'm treating greater than 80%, and I'm also treating everything to the right up to that level at 80% TSS, and a fraction of everything above that gets some treatment as well, because it doesn't just turn off at that point. But on a net annual basis, I could be sizing down here, and there could be a significant amount of water in this area with a considerable pollutant load that I'm missing because the equipment's gone into bypass. So there's more study to be done. Okay, tools. I kind of live and breathe in this world myself. I develop a range of tools for Hydro International through Excel-based spreadsheets. If you have a local regulation that you are sizing to all the time, and you want a tool that develops a solution where you can just put in a couple of numbers and it'll spit out an answer. I can do that for you. We have a lot of data. We can talk to the regulator and show what we're doing and maybe get a tool approved. So if you want a specific tool for your office, for our equipment, I can do that. Currently, we have sizing curves, we have sizing tables, and we have a range of spreadsheets. We have spreadsheets for Canada. We have spreadsheets like here for Calgary. They require a very specific sizing method and printout, and we develop a tool for that. In the Midwest, the APWA marked manual is a effluent control standard, and we have a sizing tool for that. Quebec is a different sizing standard. It would be really easy if we could standardize this nationally, but unfortunately we don't, so I spend a lot of time developing tools, and all these tools are available to you through our website. And speaking of the website, now if you download the PDF in the handout section of this presentation, you'll be able to click on these links. Now there's a bit of a hack here. Our website's a fairly big website. It has a lot of equipment in it because we do several industries. If you just go to hydrointernational.com and go up into the address bar and back out and just type in BMP sizing on the end of that, it will take you to a shortcut. And let me just see if I can get my pointer back. Let me hang on, just bear with me a second here. Okay, for some reason it's not letting me get my mouse click back, so I am going to, that's the end of that presentation. Now I'm going to go into our website now and just demonstrate a few of these tools. Well, just demonstrate one actually, but so doing what I just said you would do, I'm going to start my web browser here. And hopefully that's coming through and you can see it. So now I can go to hydro-int.com/BMP sizing. And that will bring you to this one page. And on that one page you will find pretty much everything you need for all our stormwater products. And you can just click on them, and for every product you'll get DWGs, PDFs, the sizing tools that are specific to that product for a different area. And this is a sort of a dynamic page. We update it fairly regularly. If you click on this sizing tool in the first offense, or the sizing tool there for the downstream defender, it's the same tool. It will bring you to an online tool that you can use, and you just have to log into it. And you have options to size by regulatory agency, by particle size, or to manually grab a product. I'm not going to go too much detail into this. Let's assume you just want to size. I just want to show you a couple of items here that you want to size by regulatory agency, and I'm going to apologize because nothing is working here. Let me just refresh that and see if I can get it working. Okay, there we go. So I can click on regulatory agency, I can select the regulatory agency, and let's say we go with New Jersey again. And really, because it's a pre-approved regulatory agency, all we have to do is put in our treatment flow rate. The system will work out the best device and an alternate device. If this one doesn't work for you, an alternate. And then you can, the numbers to the right are the standard numbers for the device. You don't really have to change them unless you want to. And then you can download either a standard drawing or a detailed drawing. The trick is, before you can download a drawing, you need to save the device into a project. So you can simply save this product, give it a product name. This might be manhole number 1 on your site. and you've got to put it into a project. So you can give a project name, create a project to store them. You might have multiple products on one project. In this case, I've got several here. I can just put it into an existing one, save that, and now I can download a detailed general arrangement drawing. You click on download, and it straight away should throw something immediately into your download folder. And when you open that, you have a product drawing customized with dimensions, customized with a title, project, and all that. So very easy to do. We also have a technical support group that can help you with detailed site-specific drawings as needed, and all that. So I think I've probably burned up enough of your time. I want to thank you very much for your time. We covered a fair bit in terms of toolkits. We've covered the testing, the validation, certification, sizing methods. Each one of these could be a whole webinar subject in and of themselves if you wanted to go in that detail. But really, I just wanted to give you an overview of what there is out there, all the different methods that are out there, all the different theories. There's lots of different things going on, and it really depends on where you sit and where your project is as to what method and what process we go through to get an answer. And that's our job. We help you out with that. Just contact us. So with that, I want to say thank you very much. When you close out of this presentation, you will go to the survey. Please fill that in. And as I said before, answer or fill in the piece at the end with any comments or questions, and I'll get back to you as soon as I can, probably in the next few hours, and answer your questions. With that, I want to say thank you very much and have a good afternoon.